Throughout the year, we've informally talked about limits a number of times. So let me remind you of some of the things we've done in earlier units. We added a geometric sequence where r was less than 1. In this case, r is equal to 1/2. Every time we multiply, every time we go to another term in the sequence, we're multiplying by 1/2. So the terms are getting smaller and smaller. And we looked at this little diagram here. If I take 1/2 plus 1/4, I have 3/4, and then plus 1/8, I would have 7/8, plus 1/16, and I would end up with 15/16, and so forth. And every time I add another term in the sequence, I'm adding half of what's left over in the square, and I never actually get outside of this square. So if this square is a 1 by 1 square, which is one whole basically, if I add 1/2 plus 1/4 plus 1/8 plus 1/16 and I go on to infinity, the sum actually equals 1. And I introduced in the notes just briefly this limit notation here. This is the formula for the sum of a geometric series right here. If r is less than 1, we say that s is the limit as n goes to infinity of the sum of n terms. Well, as n goes to an infinite number of terms, there's an n right here. I raise r to the infinity power, basically. So if I say 1/2 multiplied times itself an infinite number of times, that's basically 0. And so this whole numerator simplifies to just a sub 1 over 1 minus r, and that was how we found the sum of an infinite number of terms. Only worked if r was less than 1. Another example was when we looked at this formula for compound interest. If I start with a principal amount of P, say $2,000 or whatever, and I have an interest rate of, say, 5%, and I add that interest rate once a month, like, so n would be 12, I add it 12 times a year, and then T is how many years, this formula would tell me how much money I would have at the end of the 12 years, or if I have, say, 5 years, and I add it 12 times a year, interest rate of 5%, this tells me how much I would have at the end. Now, I found out that if n gets infinitely big, the formula becomes this formula. Well, notice we have some commonalities here. This is still the amount I have at the end. P is still the amount I had at the beginning. I still have an interest rate r and a time t, which is these values right here. You know, I'm kind of covering that up, so let me get those off of here and just point to them. Okay, so I still have an interest rate r and a time t. But what's different is here I have an e as my base, but here I have this thing right here. I've accounted for the r and the t, so what's left over is that I have 1 plus some, 1 over n to the nth power. And I found out, or we found out on your worksheet, that if we took bigger and bigger values and put them in for n, so here I'm putting 100 in for n, here I'm putting 1,000 in for n, here I'm putting 10,000, 100,000. As e gets bigger or as n gets bigger and bigger, the number that this quantity equals turns out to be the number e, which is 2.71828, on and on and on for infinity, an infinite number of decimal places. So we say e is the limit as n goes to infinity of 1 plus 1 over n to the nth power. So there's another example of a limit. A third example of a limit was when we were looking at how to find the area of a non-right triangle using trigonometry. So we have this triangle here. It has an angle, turns out to be a 45-degree angle in this case, and it has a base of 10, and we need to find the height. So if we drop a perpendicular line here, we could say sine of theta is h over 10, or h equals 10 sine of theta. So the altitude here is 10 times sine of theta. The base is 10. Area of a triangle is 1/2 base times height, so it's 1/2 times 10 sine of theta. Now, if we keep if these two distances always stay the same, which they will in a circle, these are all the radius of the circle, and the only thing that changes is theta, then I can find the area of a triangle with any angle theta using this little relationship here. So for 8 triangles with an angle of 45 degrees, I would have the total area of this whole polygon would be 8 times 1/2 times 10 times 10 times sine of 45. Then if I would subdivide this into 10 triangles instead of 8, each triangle would have an angle of 36 in it. There would be 10 of them, and I would use this. And I kept doing this using more and more sides of the triangle, smaller and smaller angles, and we end up with this formula that says we take 50, sorry, 50 is just 10 times 10 times 1/2 times whatever n number of triangles we have times the sine of 360 divided by n. What happens as n goes to infinity? What happens as, if I think of this as my, if A is the, what does A represent here? Oh, never mind about that one because I can't remember what it represents. I think A is the, A is the angle. So here we have A is the number of degrees. So if we use the number of degrees as A goes, as the actual number of degrees goes to 0, the angle, sorry, in here goes to 0, or if the number of triangles goes to infinity, we end up with that the area is equal to the area of the circle. And there's actually a cool little animation I can show you about that. So if we go down here, okay, here's just our triangle divided in, our circle divided into 6 equal triangles here. And again, now if you watch this, it's going to start out with 6 equal triangles, and then it's going to divide into more and more triangles. And over here, we're looking at, if this is just a circle of radius 1, then its area would be pi times 1 squared, which is just pi. And so if we look at the approximation to the area here, it's getting closer and closer to pi the more circles we have in here. So using more and more triangles, we get the approximate to the area. Using more and more triangles, it gets closer to pi, and we start over and over again. Excuse me. Now going back to our last example is an example that we haven't seen yet. So these are just examples of things we've seen. So you can see limits basically saying as something gets increasingly big or increasingly small, a quantity approaches a certain number. So here's a calculus example. In calculus, there's 2 big quantities that we're trying to find values for. One of them is, what is the slope of something that's not linear? So for example, if I ask, what's the slope of this function? Well, it's obviously a variable slope. It changes as we move across this function. So we're going to learn how to do that, and that's called the derivative. We're going to at least get the beginnings of how to do that. The second one is, what is the area under this curve? So if I, and I'm specifically saying the area under the curve from 0 to 6, somehow that kind of got messy right there. So from 0 to 6, what is the area under the curve? So from here to here, this is 6. What is the area that's enclosed by the x-axis, the y-axis, and this curve? Well, if it was just a box, I could easily find the area. It's just the length times the width, or the height times the width in this case. But I don't know how to find the area of a curve of a curve that I'm not familiar with like this. It's not a circle, for example. So one method of finding the area is to estimate it by drawing rectangles. So I'm going to draw a rectangle, the top right corner of which is a point on the graph. Okay, so I'm going to draw a series of rectangles. Notice they're all the same width. Okay, they all have a width of 1. And I'll draw another one here, and another one here. And notice I'm always using the top right hand corner is just going to be a point on the graph. So if it's a point on the graph, I know how tall the triangle is, and I know that it has a width of 1. Sorry, the rectangle, and I know it has a width of 1. Oops, that does not correct that last one I just did. So let me fix that. So I'm taking the right hand corner. Okay, so notice if I were to shade in all these boxes, notice some of the boxes, some of these rectangles are higher than the curve. Most of them are lower. The first rectangle and the last rectangle have a piece that is above the curve, and then this is almost equal, these two, and then these two have pieces that are less than the curve. So if I were to take this triangle here and substitute it into here and this one into here, we would see that the area under the curve is pretty closely approximated by these rectangles. Now in calculus, so we're saying the area is approximately equal to the sum of the area of the rectangles. Now, how could I make this approximation even more precise? Well, I could draw skinnier rectangles, because the more rectangles I draw, the more closely these rectangles will fit the curve, just as if I put more triangles in here, the more closely the edge of the polygon would fit the edge of the circle, with less waste left over. So if we look at this, I've got a little animation or a little applet that explores this. So I'm going to change this to the equation that I'm using here. I'm going to use the type of function or type of the rectangles where the upper right hand corner is matched up with the graph, and I'm going to set this so that it matches 1 through 6, and then I have 6 rectangles. So this is what I drew. Here is this Riemann sum is the area of all the rectangles added together. So that's right here. The exact integral this is a calculus concept. This is exactly the area under the curve. This is something you learn to do in calculus. So what would make this Riemann sum, the sum of the rectangles, more exactly, more close to the exact area? Well, if I increase the number of rectangles. So look what happens to the Riemann sum as I increase the number of rectangles. And look at the picture too. The smaller I make the rectangles, the more the edge of the rectangles approximates the actual curve of the graph. So with 20 rectangles instead of 6, the difference between the sum of the areas of the rectangles and the true area under the curve is now very small. There's very little difference. So we could say, as these rectangles get smaller, narrower, and narrower, the area under the curve, the sum of the rectangles approaches the area under the curve. So as the width of the rectangles approaches 0, the sum of their areas approaches the true area under the curve. Or maybe I should say the area under the curve. Area under the curve. In limit notation, we'd say the limit, we'll call this x here, as x gets close to 0 of the area equals maybe the true area. Okay. Now this is just a kind of a brief introduction to what limits are. Limits are, we're changing something, we're moving something, there's a dynamic quality to this. As something is changing, as one quantity is changing, how is another quantity changing? That's basically what we're going to look at. And then we're going to look at a very specialized application of a limit where we use what we know